All right, buckle up. We're in for a long one on this one. Weak acid and base equilibria. So this is where it gets more and more complicated. So we'll start off with acids, more common than bases. I think in almost all cases, acids are more common. So weak, we can see that before we only have the weak acid. Afterwards, a little bit has ionized into the proton and its conjugate base. Generally, we think of as less than 5%. There's no real, solid part to that. Usually where that comes around is vinegar or acetic acid. We usually say 5% in solution as a generic term. Small Ka, more reactants, pretty easy to see. Dissociation constants. So now we need to get into the ideas of what Kas are kind of small. These are pretty small. They get much lower. Some of them get crazy low. Again, when we think of these acids and bases, you need to know you're strong. So therefore, if it's not strong, it's by default weak. The conjugate base is always just take away a hydrogen. So don't get too over worried about that. And again, if you have a base, the conjugate acid is another hydrogen there. I don't think you need to understand the names. You might just pick up a few from time to time. And don't be worried about, again, they're not about memorization of what these are. I think they used to be, but not anymore. So these Ka values would be, of course, provided, but you need to understand what do each of these mean. So if you have a smaller Ka, then, a larger Ka, see how easy it is, than a smaller one, this is more acidic than this is. Okay, this is providing more products, more H plus, than this is down here due to the negative exponent. Bigger negative exponent means less hydrogen in solution. Smaller, or I should say smaller exponent, then again, we're not talking about the negatives. These are always going to be negative. So again, numbers, being comfortable with those, that's going to come up in easy questions to come across. So an example of a problem here. pH of this weak acid, and it has a Ka value. Sometimes you can even luck out in knowing that it's a weak acid because they give you a Ka. That is, of course, small. They're not going to give you a Ka that's going to be like 10 to the fifth, unless they're asking some real more hypothetical question that's not too common, which they can. pKa, this comes up quite a bit. Again, P just is the negative log of that Ka value. So we've got our dissociation question. The Ka values are referenced unless they want you to find it. That's not as common though. So you set up your equation, then you ice it. Again, you have your original. Of course, you didn't have any in solution. Now you might say, well, wait, didn't you have some of this because it's in water? Yes, times 10 to the negative 7th. So when you add these up, insignificant. Yeah, that's why you can just put it at 0. We have this stoichiometrically break down. And so this should look pretty familiar from equilibrium. You put those together, and so you have 0.5 minus x. Now look at how much becomes this idea, 10 to the negative 5th. That's going to be super small, okay? And that's pretty much going to be super small as a general default, unless there's something to where the Ka is very, very high, which is very unlikely. You can use the 5% rule. K is very less than 1, at least 1,000 times smaller than the initial. Okay, so we can drop that off. So a lot of these are going to be your x squared over the initial concentration. I think I was finding myself doing that on a lot of the Pearson problems because I'm like, okay, it's another one. Okay, it's another one. Okay, it's another one. But of course, you're going to be experiencing this on the AP exam, which I'm not even sure how much they scramble it up. If you're going from a Unit 2 problem to a Unit 9 problem to a Unit 4 problem to a Unit 2 problem again, it's going to be all over the place. They don't just go unit by unit. So keep that in mind as you're going through, though. This is going to be an insignificant x. All right, so then you put that in, solve for your hydronium. You've got your hydronium. But again, make sure you're solving the actual problem, pH. Negative log of that, 4.52. And one thing you can always do is, of course, you're dealing with an acid. It should be under 7. It is under 7. It's a weak acid, so it should be closer to neutral than very acidic, like 1 or 2. So this makes sense in a general fashion. It's very easy that if you get one exponent wrong here, one higher here will get you one higher here, right? Because this is a logarithmic scale. So weak bases with water, similar but different. You got your conjugate acid and your hydroxide instead of hydronium. Kb value for this one, what would this one be? CH3 and 2? Methylamine. Okay. I understand weak base is far less than conjugate than weak acids. Weak acids are much more familiar to me. But again, you're dealing with the same. Products over reactants equals your Kb. Again, this tells us all about hydroxide. So when you're seeing bases, it's always good to just write a big hydroxide on the problem so you know you're getting information from that. So a lot of students struggle to identify weak bases and their conjugate acids. So the weak base, you might notice a pattern. I don't know. If you're looking at these, you might notice some kind of, there's nitrogen involved. Very good. Along with some other hydrogens that may be gained or lost. You can also see there's a bunch of carbon-hydrogen chains as well, or maybe another nitrogen. But to me, they don't look like acids. They don't even look like weak acids. They got a whole bunch of nitrogen involved, okay? So conjugate acid, add a hydrogen to that area to where there's the nitrogen. So all you do is you add that hydrogen to there. Now, looking at our KBs, right? If we have a large KB here, that means there's a lot of hydroxide in solution. So a lot of hydroxide in solution means less hydronium. So this one is a stronger, or I should say higher base, stronger base than like this one is. That makes sense. So that means that if this is a stronger base, its pH is higher. This pH is lower. You can go about and take any Ka and Kb because you multiply, and again, these are all dealing with in aqueous solutions in water. Ka times Kb equals 1 times 10 to the negative fourth. That's what we had for water, right? The acid and the base, H plus and OH minus, same idea. So sometimes you're given the Kb and they want you to talk about the acid part. You just have to do the quick math to get to the Ka, and then you can do it all from there. Again, these are reference values unless you're trying to find it. Then you just plug in your concentrations and you're there. So the reaction in general, you got your base, those ones that are funky, plus water, makes the base with a hydrogen and your leftover hydroxide. So this is the general setup. All of them really do it. Don't really get caught up in it, but you've got your weak base with the hydrogen, hydroxide all over the initial concentration, or what you have is the concentration of the weak base. So that's just the way they go. So a problem, same similar idea. 0.5, you got a weak base because it's got a whole bunch of nitrogen in it. You got your Kb. Remember, it's just a negative log. You've got this, again, you're producing two of these. Bases add a hydrogen, leaving the OH, okay? Ice it again. We got the same ideas. Guess what? X is really small, order of 1,000. K is less than 1. Again, that's going to be your norm. You'd have to have a very close Kb to your initial concentration. Now, this is like 0.00005. Yeah, now you're going to start dealing with that, but that's going to be super rare, okay? Just keep an eye out for it. Again, you got your K squared, solve for that. Your hydroxide concentration is 3 times 10 to the negative third. We need to get pH. You can do this as the POH, no problem. 14 minus gets you 9.48. So you can do a lot of these things here. You can have, if you wanted to go back, you could have this. You could do the Kw to determine the hydronium concentration and do the negative log of that. You could go many different ways. There's no wrong way to do it. Just want to make sure you show your work in doing it. Remember, you can convert back and forth from Ka and Kb. You just use the product of water. if you're given Ka, remember, again, go back to that what you need. Now, these types of problems will not be done with a different Kw. You could, it'd be just a different number, but they're not going to be. I've never seen any ones to where you're dealing with this just as problems by themselves. Keep also a note that, what was I going to think of? I can't remember what I was thinking of, but I think I was trying to get to the next slide, which is a little addition from all of this because it seems kind of out of place. And that's called percent ionization. Okay. So strong acids, 100% for the first hydrogen, right? And then the other ones are going to be so insignificant. Bases are easily 100 to 200%. And again, we're talking about this for a strong acid or base. Depending on how many hydroxides are present in the original, if you had calcium hydroxide, CaOH2, then you're going to have twice the amount, right? Now, if it was weak, we'll need an ice table and solving for it given the original base and acid concentration. So that'd be a little more complicated, like if when we went back to, if I look back at like this one here, maybe back here, where we solved for what X is, we need to see our original concentration, 0.5 minus this. That might be so insignificant it might not even show up. But again, we would need to have our concentrations in there because this would also be the concentration of ammonium in order to see what is the percent ionization for that. I remember what I had for here. We talk about this not being at a kW, other than 25 degrees Celsius. But in reality, and again, you won't be doing this at the AP exam, when you mix an acid and a base, heat is released. Therefore, the temperature always rises. So if the temperature always rises, guess what? These values become very different than what we kind of train you with at these. That's what it was. Okay, back to this. So you have a very simple formula. Concentration of the ionized over the initial. So your hydronium over your hydroxide. Or again, keep in mind, hydronium over concentration of the acid. And again, base over that. Again, they often ask for the hydronium concentration. But keep in mind, sometimes you are given the percent ionization and they want you to solve for this. So in any of these equations, you should be able to solve for any of the unknowns. Now, one of the things that comes up here, wanting you to think about, higher the concentration, the lower the percent ionization. Okay, so when you have higher concentration, you get more hydronium. You can totally see it. But the percent that ionized is a smaller amount. It's a volume, right? If your initial molarity is high, that's going to make this value small, even if this is larger, because no matter what you started with, HNO2 is going to be, this is a weak acid. That means this fraction of this is going to become hydronium, which you see. So therefore, you're taking off this increased amount, but you're really shaving it down to very small based upon the very small Ka. So which one is more acidic? This one is more acidic because it has more hydronium in solution. However, its percent ionization is lower. So just keep those in mind. Again, the bigger the concentration, the smaller the percent ionization. Again, though, bigger the concentration, the more hydronium you have in solution. More acidic it is. Okay, so if we were to look at a pH of these, this would have a lower pH than this. All right, so keep that in mind. They're going to ask questions about percent ionization, so just be on the lookout for it. It should be something easily obtainable. All right, coming with your questions, and we're on to the next.